Hello students and welcome to Unit 1 Part 3. This will be your first and only lesson in this part of the unit. In this lesson we are going to put together all that we've learned in Unit 1 as we compare real numbers. Our essential question for today is how can I compare and order real numbers? So let's first think about what we have learned since we are putting it all together today. The first thing we learned was that real numbers are all the numbers that can be represented by our world's phenomena. We then learned that some real numbers are rational, meaning they can be written as a fraction. This includes integers, fractions, decimals that repeat or terminate, and perfect square and cube roots. We also learned that some real numbers are irrational, meaning they cannot be written as a fraction. These include decimals that do not repeat and do not terminate, including pi, and non-perfect square and cube roots. What all of these things have in common is that they can be written as decimals. This is going to be the basis of what our lesson is going to deal with today. We can use this fact that we can write all of these forms into a decimal to compare two or more real numbers as less than, and here's the symbol for less than, greater than, or equal to. We are going to look at three different scenarios in this lesson. We are first going to look at identifying a location of a real number on a number line. We are going to look at comparing two amounts as less than, greater than, or equal to. And last, we are going to look at how can I order numbers from least to greatest. So let's start with our first goal of the day, and that is to identify a location of a real number on a number line. Here you can see a number line that stretches from -11 to 12, and there are bigger and smaller number lines, but all of ours are going to fit on this number line today. So here are steps to identifying the location of a real number on our number line. First, we need to convert our real number to a decimal. Second, determine where that decimal would lie on the number line. And third, plot a point for your real number and label its value. So let's look at our first example. Our first example is -5/8. So our first step is going to be that we need to convert this fraction, which has a negative value, to a decimal. To do so, divide. Remember, the numerator always enters your divide box. We're going to put 5.00 because that will give us two decimal places and we can use one of them to round. 8 is always our divisor, the denominator. Will 8 go into 5? No, and that makes sense because this fraction is less than 1, so we're not going to have a whole number. 8 goes into 50 6 times, which is 48. We have 2 left over, bring down the 0. 8 goes into 20 2 times, which is 16. 4 left over, but this gives us a good idea of where this number is. Since it has a negative value, we'll add that negative to the inside, to the number, and we get that this is about -0.62. Well, where does -0.62 lie on the number line? Between 0 and -1. So I'll put a dot here, a little over halfway, and I'll label it. This is -5/8. Notice I numbered it, I labeled it with my original value, not my estimation. Let's try another example. The square root of 56. Now, I know my perfect square roots, and I know that this is not 1, because this lies between the square root of 49, which is 7, and the square root of 64, which is 8. So this amount is between 7 and 8, so it's 7 and I'm going to make a fraction bar to determine about how much it is. Now, if you look at the first perfect square root and our non-perfect square root, there is 8 difference in its value. If you look between the two perfect square roots, there is a 15 digit difference. Now, write that as a fraction. We have 8 over 15, and now we can estimate its value. Divide 8 by 15, add 0.00 so we know how to round it. 15 will not go into 8, which makes sense. Here's our whole number. We're not getting the whole number from the fraction. 15 will go into 80 how many times? 5 times, which is 75. There's 5 left over. Bring down the 0. 15 will go into 50 3 times, which is 45. And again, there's 5 left over, but that's okay. We have enough to round now. We have 0.53, which is about 0.5, since it does not round up. But instead of writing 0.5, I write 7.5. So this is about 7.5. So where does 7.5 lie on our number line? Here between 7 and 8. So the square root of 57 would lie here between 7 and 8. Let's try another example. 2 to the negative 3 power. Now, you know integer exponent rules, and you know that when you have a negative exponent, you need to move that value to the denominator in order to make the exponent positive. So this will become 1 over 2 cubed. Now, what does 2 cubed mean? That means 2 times 2 times 2. 2 times 2 is 4, times 2 is 8, so we get 1 over 8. Now we convert that to a decimal. 1 inside, 8 is our divisor. Add 2 zeros so we know how to round it. 8 goes into 1? No. Which makes sense because remember, negative exponents in the numerator indicate a very small amount. 1/8 is a small amount. 8 goes into 10 one time, which is 8. There's 2 left over. Bring down the 0. 8 goes into 20 2 times, which is 16. If we went out one more digit, we would get a perfect value. Because 20 minus 16 is 4. Bring down your 0. 8 goes into 40 5 times evenly. So we get 0.125. There's no whole number because this is a fraction less than 1. So we get 0.125. Where would 0.125 be on the number line? It'd be here, close to 0, but between 0 and 1. So here is the value 2 to the negative 3 power. Notice I labeled it with my original amount. Here we have another expression with an integer exponent. Here we have a negative exponent in the denominator. We know that to make that a positive exponent, we need to move it to the numerator. The 2 will stay in the numerator because it has a positive exponent of 1. So we'll have 2 times 3 to the first power. We know that 3 to the first power is just 3, so 2 times 3 equals 6. So on the number line, here would be our value at 6, and that would be the same as 2 over 3 to the negative 1. Alright, let's look at our second goal of the day. Our second goal of the day is to be able to compare two amounts as less than, greater than, or equal to. The steps for doing so is to first convert your real number to a decimal. Second, compare the two decimals as less than, greater than, or equal to. And third, compare the original numbers with the same symbol. Let's look at an example. So in this first example, we're asked to compare the square root of 40 and 1.6 divided by 2 to the negative 2. Our first step is going to be to convert those to decimals. So the first thing we need to do, we have the square root of 40. We'll have to determine what two square roots it's between. Well, that is between the square root of 36, which is 6, and the square root of 49, which is 7. So that makes 40 6 point something, or 6 with a fraction. The difference between the first perfect square root and our non-perfect one is 4 digits, and the two perfect square roots is 13. So we get 6 from being between 6 and 7, and 4 thirteenths. Now we'll divide 13 into 4.00 to determine about how much this fraction is in terms of a decimal. 13 will not go into 4, which makes sense. Here's our whole number. We're not getting that from the fraction. 13 will go into 40 3 times, which is 39. There's 1 left over. Bring down the 0. 13 will not go into 10, so put a 0 there. So this is about 6.3. 6 from being between 6 and 7.3, because that's the approximation of this fraction. So we're talking this is about 6.3. Now let's figure out what this is equal to. We have 1.6 over 2 to the negative 2. Now we know that a negative exponent in the numerator can move to the denominator to become a positive exponent. The 1.6 will stay in the numerator because it has a positive exponent of 1. So we'll get 1.6 times 2 squared. Again, changing that exponent to a positive. Now, order of operations says we have to do the exponent before the multiplication. 2 squared is 4. So we get 1.6 times 4. 1.6 times 4, if you did on the side of your paper. 4 times 6 is 24. 4 times 1 is 4, and 2 more is 6. 1 decimal place, we get 6.4. So this is equal to 6.4. We can now compare them. How is 6.3 compared with 6.4? Well, 6.3 is less than 6.4. So that means that the square root of 40 is less than 1.6 divided by 2 to the negative 2, comparing the original amounts with the same symbol. Let's look at another example. We have 2 times the square root of 5, and we have 4 3/8. Our first step is going to be to convert them to decimals. So first, we're going to have to do 2 times the square root of 5. To do that, we're going to first have to get the square root of 5 to a decimal. Well, I know that that's between the square root of 4 and the square root of 9. So that makes this between 2 and 3, or 2 and something. 4 and 5 have a difference of 1. 4 and 9 have a difference of 5. So we get 2 and 1/5. Now convert that to a decimal by dividing 5 into 1.00. 5 will not go into 1, which makes sense because here's our whole number. 5 will go into 10 2 times, which is 10. Nothing left over, nothing more that we have to bring down, so we get 0.2. So the square root of 5 is about 2.2. But our question did not just say the square root of 5, it said 2 times the square root of 5. So we can do 2 times 2.2. 2 times 2.2 is 4.4. So this is 4.4. Just because we are nearing the 15-minute mark, let's go ahead and use the calculator to divide 3/8. 3 divided by 8 is 0.375. So this is 4.375. And now you can see that 2 square root of 5 is greater than 4 and 3/8.